Hello, everyone. One of the most important parts of any machine learning project is to be able to understand and summarize data structures. This means that we know what input features we have and the types of data that we have to work with, and also be able to find target variables or outputs in our dataset. Recall that one of the main goals of supervised machine learning is to find a mapping or function between input features and target variables. Therefore, it is critical to be able to distinguish and separate these two parts from a given data set, which is usually in terms of a CSV file, especially if you're working with tabular or structured data sets. And in this case, we can also use tools from descriptive statistics to summarize data, meaning that we can find distributions and relationships in data, and also to have nice data visualization techniques, such as correlation matrices that we're going to discuss in this video. To get us started, one of the easiest way to import a CSV file is using Pandas library. In particular, in Pandas, we have something called pandas.readCSV. So this is a method that is inside this Pandas library. And this allows us to load CSV files or comma separated value files into a Pandas data frame. And a Pandas data frame is pretty much look like a Excel a spreadsheet where we have columns and we have rows. So in order to become familiar with the exact syntax and how to use read CSV, you can go to this link and I can click on it. And you can see that there are so many input arguments here. Usually we only need to work with a few of them, and these things are at the beginning of the list, meaning that the most important thing that when you want to read a CSV file is to give the file path to that CSV file. So where that CSV file is located, and then Pandas will be able to go and read that CSV file. We also have a few other options here too, right? So how we have the data in that original plain text file separated. Usually it's commas and also with the header. So we have the first row, which is the column names, and how do we have to sort of like find them. This is something that automatically has this option called infer. So this means that you don't have to specify this, and by default, the first row, that's the header, which are the column names that we have. But you can see that if for some reason the data has been stored in a different format, you are going to be able to specifically define the header. The same thing also, for example, with these use columns. In this case, usually when we have a small data set, which we work in this class, we import all the columns at the same time. But in a real world machine learning problem or data science problem, you may have thousands of columns or different types of features, and therefore you may just want to work with a subset of them to save space and time. So going back to the original Jupyter notebook, here I have the main syntax in terms of the things that we really need to know for this course. The first one, again, is the file path, the delimiter, the way that we separate the numbers in the original plain text file, the row number to use as a header, and this already has a default value, so you don't have to specify this. And the same thing with index columns and use columns. So these things will get a little bit more clear when I import this data set. So you can see that in this case, I'm using pd.readcsv file. And this file is located on my GitHub page. So here you can see that this auto.csv is the CSV file that we have. And I have provided the link or URL to this CSV file. And in this case, I'm printing this data frame, which I showed that using the variable df. And you can see that we have 397 rows. So this means that we have 397 vehicles in this data set. And we have 9 columns. And here you can see that the goal here is to be able to have a predictive model to to make predictions about the MPGs of new cars given these predictors or input features. And all of these things are now included in one data frame. So one thing that we have to do at some point is to separate this target column from these input features that we have. But at the same time, you can see that some of these are not immediately like usable for us. For example, the names of the cars are character strings. They're not even numbers. And we cannot provide this information to, let's say, a linear regression model or just a machine learning model, because in most cases we have to work with numbers. So this means that most likely at this point, we have to discard this name column that we have. And we have to also do more analysis on the remaining columns of this data frame. In order to do this, one of the most important parts is to get more information about these column names. And this is very important because now we can retrieve one column by just providing the name of this column. And also we have these index rows here. So in this case, the index rows are simply some ordering of these numbers from 0 to 396. That's why we have 397 rows here. And remember, indexing in Python starts from 0. But just to make sure that that's the case, so we can use this attribute of this data frame. So remember, now we are working with object-oriented programming. And if I look at index, it says that this is basically a bunch of numbers from 0 to 397 with a step size 1. So 0, 1, 2, 3. And the way that indexing works in Python, the starting point is always inclusive, but the stopping point is exclusive, meaning that the last item here you can see is 396. So this means that up to 397, but not including 397. So these are the index rows that we have. And also we can look at the column names too. So in this case, if the data frame is too large to be able to display that in a sort of like Jupyter notebook here, you can make sure that you actually have all the columns that you're looking for. The other method that you can use once you have your data frame df here is use this .head method. And this by default shows you the first 5 rows of this data frame. And this is very helpful so that you know how your data frame looks like. Obviously, if you want to look at the more rows of this, you can always change this here. So you can, for example, say 10. So you can see that now we have the first 10 rows, but the common thing is to just not provide any inputs. And by default, this will show you first 5 rows. Another thing that we can use once you have a data frame is this .info method, which provides you a summary of a data frame in terms of specifically the number of non-null values. So this means that the values that they are not empty. So we have 397 values for each of these columns. And here also we have D type, which stands for data types. You can see that MPG is a floating number and the number of cylinders. So that's usually an integer. So you can see that here. The same thing with displacement is a floating point number. And also, for example, with name, you can see that here we have character string. So that's why it shows you here object. And if you want to look at like, let's say the first row of this data frame and also the value of the horsepower. So what this does here, so right now, if I just use df and then provide this column name, I retrieve all the information for these different values of horsepower. And if I put this .ilog0, this means that I want to only look at the row with index 0, which is this 130. And that's what you get here. And the reason that I wanted to do this is that if you look at horsepower, there is something strange about this, that the horsepower in this .info method that we used is an object, is not a floating point number or an integer. And here also you can see these quotation marks here, which shows that this doesn't look to be an integer. So if you're not sure, you can always use the type function. That's something that is defined in Python. You can use it on any object in Python to see what the type is. And indeed, this is a character string, right? So this means that this is text, it's not a number. But this is one of those cases that we can easily convert this actually to a number. And the way that you can do this in Pandas when working with data frames is there's this method called toNumeric. So this means that I know that this column includes objects of the form character strings, but please convert these strings to numbers, right? So that's what this PD toNumeric here will perform. And there's also an option here to say that how you want to deal with errors. And what does this mean? So if for some reason, let's say one element of this column is something like a question mark or NA or some, letters, we cannot convert those to numbers. So what should we do? Should we get rid of them or, how should we, deal with them? And this errors equals to core errors. What it does, it converts them to nan, which basically means not a number. That's what it stands for. So it's a nice way of saying that, well, that column does not have a number. And if I run again, so already I converted this horsepower column to numbers. You can see that now even have 130.0. So this means that now this is a floating number. And if I run this .info method once again and look at horsepower, you can see that now this is floating point number. That's exactly what we wanted to do. However, you can already see that there are 5 elements that they are kind of like missing or they're not a number, right? That's what it was when we use this coerce equals arrows equals to coerce. This means that if we cannot convert it to a number, then we use nan, not a number. And this tells us there are 5 elements that are not a number. And in order to, double check this, you can actually use this .isNull method. And this will give you true if that element of the column is actually nan or not a number. And then I can use .sum because now all the truths will be converted to 1. And this gives me the total number of cases that I have nan values. And this is consistent with what we saw here. So there are 5 elements that are missing. And this is something important to catch this at this stage because later on, if you provide this to a machine learning model, you will get some error messages that, oh, I don't know what to do with these numbers because they are not actually numbers. So that's what we are trying to do here to remove them as soon as we can. Therefore, in order to do that, we can use this method called drop_NA, which means that we remove rows with at least one nan or not a number in it. And then we call this df cleaned. So this means that in this case, now we have a clean data frame. So obviously, we are going to remove those 5 rows across the entire data frame. So you can see that now we have 392 values for MPG, cylinders, displacement, horsepower, and so on and so forth. The other thing that we also want to do here is to drop that column that was called name, because again, those are character strings. We cannot convert them immediately to numbers. So it's just for now, we want to drop that. And so you can see that now df clean has this MPG column and then 1, 2, 3, 4, 5, 6, 7 other columns. So once you want to get to the point that we use descriptive statistics, you can use .describe method on your data frame. So you can see that now for each column where we have numerical values, you have information about the number of elements that we have, the mean or average, standard deviation, min and max, and also quartiles, right? So the 25% percentile, 50%, and 75%. So this gives you a good idea about the distribution of your data, meaning that do we have skewed distributions or do we have extremely high standard deviations? And also the scale of these or range of these features. So you can, for example, see here that this placement is the average value is 194, whereas the average value for cylinders is 5. So that's something to keep in mind, so that we have these notable differences in terms of range of values that these features can take on. One thing you can do to make this easier to visualize, obviously this is a really nice table in terms of giving us a lot of information, is to use the histogram plots. And Pandas data frames are very smart in the sense that when you just say .hist, it will give you the histogram of all these features that we have here. So now you can see more easily things such as whether, for example, MPG in this data set, does it have a skewed distribution or not? So obviously you can see here we have this tail of this distribution. So this is a skew to the right as we expect. So there are only a few cars that have really, really good MPGs, where most of the cars are in like below 30 or so. And the same thing with cylinders. For example, this is actually called a bar plot, but bar plot and histogram plots are very much similar, except the fact that bar plots are more practical for discrete random variables. Nevertheless, you can see that we only have a few cars in this data set with 3 or 5 cylinders. And that's a decision that we have to make. Do we want to keep this in our data set in terms of training and evaluating our model? Or do we want to just, ignore these few data points and make sure that we have a more sort of like, balanced analysis, in the sense that we use only data points where they are represented enough in the data set. So here is again like the overall information about the distribution of these input features and the target variable, which is MPG. And you can also continue doing these. For example, one other option is to plot what is known as the correlation metrics. And one way of seeing this is by importing this library called Seaborn. So you have to probably install this if if you get an error message here. So that's what I've done. I went to the Seaborn library, and I just installed this. For most libraries, you can do this easily using like the pip install Seaborn. So pip is package installer for Python. So it's a way of installing packages in Python, and that's should be relatively straightforward. And once you import this Seaborn library as SNS or any other name that you want, you can use per-plot and provide the entire data frame that you have. So this may take a few seconds because you get a lot of information here, but this is very actually interesting in a sense that what you get here is that you have all these columns in your data frame on this X and Y axis. It's kind of like easier probably to explain this for the origin. So here when you have origin on the X-axis and origin on the Y-axis, so this means that you're actually looking at the histogram plot of origin. That's what we had here too. The same thing with other histogram plots. These are on the main diagonal, so year and year. Then, for example, we have weight and weight. So these are the histogram plots. You don't have to plot them separately. And then also you have these scatter plots, right? So for scatter plots, you can see that now, for example, you have origin versus MPG, year versus MPG. So each data point here has one X value with MPG and one Y value with year. And so here we have 392 data points, so there should be 392 circles here. And some of these reveal very important information, right? So again, the first here is MPG. So it tells you that as, for example, as let's say go with horsepower. When MPG is high, then horsepower is usually small, right? And that's something we expect, right? The more like efficient cars, they usually have small horsepowers, right? They are not super fast. The same thing with weight of a car, right? So as the weight of the car gets smaller, then we expect that the MPG should be closer to like 40 or something like that, right? So you definitely see this negative correlation between displacement and horsepower and weight and MPG. And if you want to kind of like summarize these correlation coefficients that we have here, and here's the definition actually. So how do we find correlation coefficient between two vectors or here two columns of a data frame? So if we call one as vector X, the other one as vector Y. So each of these vectors here, um, they have 392 elements because we have 392 observations in our data set. And then we can find the Pearson correlation coefficient using this formula, where in the numerator, we have these like cross or dot products, right? So we find the sample mean or the average of all the elements in X, which is X bar, the average of all the elements in Y, which is Y bar. And then we subtract each Xi from X bar and each Yi from Y bar. And we do these multiplications and add them together. And then we normalize these by a term that looks like very much like a standard deviation of X, except that this is scaling factor that we do not have here. And the same thing with here, that's the standard deviation of Y. And we know that this number is between 1 and -1. So 1 represents perfect positive linear relationship, and -1 perfect negative linear relationship, and 0 means that there's no linear relationship. So in this case, obviously we can see that there is some negative relationship between displacement and MPG, similarly with horsepower and MPG. But to make this more sort of like obvious, one thing that we can use is that once we have our data frame, which is called df_clean, we can use dot core, which just stands for correlation coefficient. And this will give you all the pairwise correlation coefficients, similar to that pair plot that we had, but now we have the actual correlation coefficients. And inside this Seaborn package, there is a method called heat map, which provides you a heat map of these correlation metrics. And heat map, in simple terms, means that you're going to have a color-coded metrics, right? So you know that each variable has correlation 1 by itself, right? So that's something that is obvious that we have 1 on the main diagonal here. But you can see that, for example, with MPG and here like cylinders, displacement, horsepower, we have negative correlation. That's what we saw from this per plot that we had before. And also you can see that some of these input features like cylinders and displacement and things like that, they have positive correlation. So this tells us that this is a relatively difficult problem in the sense that we have to deal with something called multicollinearity, meaning that some of these input features that we have here, if our goal is to predict MPG using the rest of these features, some of these features are very much related to each other. So they are not independent by any means. And therefore, we probably don't need all of them. And some of them are redundant. And for this reason, what we really, want to do is later on, if you want to like, let's say predict MPG, in this case, I want to keep, let's say 2 of these features only, right? So obviously we don't need all of them, and only keeping a few of these here, let's say 2, should give us a good machine learning or predictive model. But something also I want to do is, again, to look at a little bit more in details at the origin and cylinders feature. So if you look at origin and use this value counts, so this is gonna count the number of times we have 1, 2, and 3 because there are only 3 values that this origin can take on in this data set. If you look at that, and based on what we had before, you can see we have 62% almost of the data has origin 1, 20% 3, and 17% 2. So overall, obviously, we have more cars from origin 1. So this is probably a country. but the imbalance is not extremely noticeable. But if I look at that cylinder column and use again the same thing with value counts and put normalized true to make sure that now we have actually percentages, you can see that we only have 1% of cars with 3 cylinders and less than 1% with 5 cylinders. So based on that, what we want to do in the next cell as a practice is to only keep cars that they have 4, 6, and 8 cylinders. So that should, easily gives us about like 98% of the data that we have. And also we want to keep only 2 of the columns for input features. So the nice thing is that here we define a function. As the input, we provide a data frame called data. So this is a function. You provide, again, like kind of like when you define a class, you provide a template. So we don't have to necessarily use the name of the data frame that we have. We are saying that if you provide an input data frame, which is called data, these are the steps that you have to take. But then later on, we can provide another data frame to this function. And what we have here is known as documentation string or doc string. And here you provide like documentation about what this code is about. So you have a data frame that's your input parameter. Then you keep cars with 4, 6, and 8 cylinders. And also we want to make sure that we separate input features and output labels, right? Because input features are always inputs to a machine learning model, and the labels are what we predict are actually outputs of our machine learning model. And what this function should return is 2 data frames, one for the input features and one for the output label. And we do this because that's a common strategy in scikit-learn, which is the most popular library for machine learning, where we should have 1 data frame for input features and 1 data frame for the targets or output labels. So the very first thing that we want to do here is to find which rows of our data frame contain cars with cylinders that they are in this set, 4, 6, 8. So what this does, it gives us a set of Boolean values, trues and falses. So true when the number of cylinders is in this set, and false when it's not. And if we pass these trues and falses to the data frame, now we only keep the rows that actually we have true in that specific row. So in that way, we can only keep these rows with 4, 6, and 8 cylinders. And then in order to find the input data or input metrics or input features, we now look at 2 of the columns only, horsepower and weight. And then for the output, we are looking at MPG. So again, this is something that, we intentionally designed this in this form that we want to have 2 input features and 1 output. So the output, what we're trying to predict is MPG, and the input features are horsepower and weight. So I run this cell to define this function. So right now we have not done anything, we just define this function. But in order to use this function, now we call it and we provide our data frame, which is called dfclean. And we assign this to X and Y. And if I run this and use the head method, you can see that these are the first 5 rows of the input feature metrics. So horsepower and weight values for different observations or samples. And these are the corresponding MPGs. The last thing we do in this video is also to plot this 3D data set. And the reason this is 3D, because we have 2 dimensions for the input and 1 dimension for the output. And the part that we have here, this is a very common thing to use for 3D plots. You're basically saying that this is indeed like a 3D plot that we want to have by using this projection equals 3D. And the main thing is to provide the values for X, Y, and Z axes, right? So you have 3 axes right now. So one is horsepower, one is weight, one is MPG. And then you use x.scatter, x1, x2, x3. Make sure you give them in the same order. And then we use the appropriate labels. So X label is horsepower, Y label is weight, and then the Z is MPG, right? So that's the common thing when we have a 3D plot, we have X, Y, Z plots. And then also we can decide in which direction we want to look at this 3D plot. So here you can see a very nice visualization of this, right? So we have the two input features on XY plane, and then the Z axis here is the MPG values. And you can see here that when we have cars with a small weight, and also a small values of horsepower, the MPG is really high. But then we get very heavy cars and cars that are very powerful, then the MPG gets very close to 15 and 10, and it definitely is much, much smaller than the values that we have for more lighter and efficient cars. So that's a 3D visualization. And the idea is that now if I have a new car where I know the values of weight and horsepower, I want to be able to predict the value of MPG. So that's our machine learning problem here, that we took all these steps to be able to provide weight and horsepower and to predict the value of MPG as the output. So since we had a very small case of linear regression in the previous module or slide, so we can think of this model in the simplest form as MPG being some coefficient or what we call as the bus or intercept beta 0 plus beta 1 times horsepower plus beta 2 times weight. So this means that once we find beta 0, beta 1, beta 2, now if I have a new car with the horsepower and weight values, I can plug that into this equation and find MPG. And one thing we have to be very careful here is this idea of multicollinearity, because we know that, for example, here horsepower and weight are not independent, right? So most cars that are like heavier, they probably have also like higher horsepowers because of the way that we want to use them. And there are several ways to, work around multicollinearity. It's always one good idea is to find these correlations using that heat map and correlation metrics and try to either remove them or combine them. Also add some penalties that we're going to talk about them later to avoid large coefficients and reduce the impact of multicollinearity. And also one other approach that we're going to take or talk about during the semester is that you can use more advanced machine learning methods, right? So obviously with linear regression, multicollinearity is a big problem because if horsepower and weight are very much related, then we cannot even uniquely solve this problem of what beta 1 and beta 2 should be. But there are some machine learning models, such as decision trees and ensemble models, that are way more robust to multicollinearity.